Hello there, welcome to section 4.6, which involves rank. In this lesson, we are going to take a look inside of a matrix, which will reveal many interesting and useful relationships hidden in the rows and columns of the different matrices we look at. To begin with, we're going to talk about the row space. So, if A is an m by n matrix, each row of A has n entries and thus can be identified with the vector in Rn. So remember, this represents the number of rows, this represents the number of columns. So a row, even if there are m rows, there are n entries in that row. Okay, then going on to the definition of row space. The row space of an m by n matrix is written row A. So row space and row A are equivalent. It's the set of all linear combinations of the rows of A. And the row space is a subspace of Rn. So note that row A is equal to column of A transpose. So again, row space and row A are the same. And so these are equal because the rows of A are identified with the columns of A transpose. Okay, so now we go on to theorem 13. It says if two matrices A and B are row equivalent, then their row spaces are the same. If B is in echelon form, the non-zero rows of B form a basis for the space of A and B. And we'll touch on that in this example. Okay, so I think that this is a section where seeing different examples will help you further understand. So we're given this matrix A, and we want to find the basis for the row space, column space, and null space. So when we begin these problems, the first thing you will want to do is you will want to row reduce this matrix to echelon form. So when I do that, I'm going to call this matrix B, and row reducing this to echelon form, I will get the following matrix. Okay. So now what we're going to want to do is look closely and utilize these matrices in order to answer some things. So theorem 13, so the theorem we just saw on the previous slide, said that the non-zero rows of B form the row space for A. So what that means is if I look in this matrix, this is a non-zero row and this is a non-zero row. So those are going to form the basis for the row space. So our basis for the row space are those rows. And we will write it like this. Okay. All right, so now we need to go on to the column space. So this is part 1, part 2. Okay, so what we want to do now is we want to identify the pivot columns in B. Okay, so here's a pivot column and here's a pivot column. All right, so the pivot columns are column number 1 and 2, right? So these columns from A, not from column B, or not from matrix B. So we're going to identify the pivot columns in B, but we are going to use those we're going to use the columns of A. And that will form the basis for column A. So the basis for column A is 3, 15, 9, and 3, 21, 12. Okay. All right, so to answer these first two questions, you can use any echelon form of matrix A. But to identify the null space, you have to have reduced echelon form. Okay, so what I'm going to do on the next slide is I'm going to take matrix B and I'm going to reduce that to reduced echelon form. So we went from A to B, and now I'm going to call this matrix C, which is the following. Okay, so if we want to find the basis for the null space, that's what we're looking for now. We have to have reduced echelon form. And you may recall that when dealing with null space, we look at AX equals 0. Well, AX equals 0 is the same as CX equals 0 in our case. This is C. Okay, so you will just use the information that we used in, gosh, what was it, section 4.3, I think, to figure this out. Okay, so if I, put these 0 columns in when solving this, then I can write my general solution. So we will say x1 is equal to negative 2/3 x3 minus 1/3 x4, coming from this first row here. x2 is equal to negative 1/3 x3. And then x3 is free. Okay, so what we will do next is find those vectors, and we get the following. So this is just calculations from, I think it's section 4.2. Okay, so if we want to find the basis of the null space, we end up with negative 2/3, negative 1/3, 1, and 0. And so this represents x3 is equal to 1. Sorry, x4 is also free. I didn't write that down. And then the other one is when x4 is equal to 1, that would be negative 1/3, 0, 0, and 1. Now, if you don't like fractions, remember you can let x3, since x3 and x4 are free, you can let them be anything you want. So if x3, for instance, is 3, then that will omit the fractions when you plug them in here, right? So then if that's 3, you would have negative 2, negative 1, 3, and 0. And if x4, if you wanted to eliminate fractions there, you can let x4 equal 3. So then you would have negative 1, 0, 0, 3. So these are equivalent. So it just depends on what you choose to be your free variable. And that will just change these entries here as well as the other entries because we'll be multiplying. Okay, and that wraps up this first example. Let's try another one. Okay, so this is the exact same thing. Okay, so this is something that you may want to try on your own. So the first thing we want to do is we want to row reduce this. So I'm just going to row reduce this to matrix B and C right away. Okay, so when I row reduce this, I get the following. This is fun. Okay, this one. Sorry I don't have some music playing for you. Okay, so now we want to find the bases for the row space, the column space, as well as the null space. Okay, so thinking back to the previous example, which is just the same, in order to find the basis for the row space, remember you want to find all the non-zero rows of B. So we have these 3 non-zero rows. So we will write them like this. Okay, and we are done with the basis for the row space. Great. Now we want the basis for the column space. Okay, so for the basis for the column space, remember what you do here is you identify the pivot columns of B. There are 3 of them, and you know what? This should be a -4. Sorry about that. So you identify the pivot columns of B, and then you use those and write down those columns from A. So we have pivot columns in column 1, column 2, and column 3. So those are the columns that are going to be the basis for the column space. Okay. All right, so now I don't have a lot of space, and I apologize for that. Now I need to find the basis for the null space. Okay, so null space. We have already reduced this to reduced row echelon form. Remember, we must have that. Okay, so now remember we solve AX equals 0, which is the same thing as CX equals 0. So we can put our 0 columns here. And then we want to write our general solution. And from our general solution, then we can write the basis for null A. All right, so remember x1, x2, x3, x4, x5. So x1 is equal to negative x3 minus x5. Okay, so I'm just solving this equation for x1 right away. Then x2 is equal to 2x3 minus 3x5. x3 is free. x4 is a positive 5x5, and then x5 is free. So for our free variables, remember, you can choose whatever you want. Typically, I will choose 1 unless fractions are involved and I want to eliminate the fractions. So from here, we will need a vector for the x3 terms and then for the x5 terms. So the basis for null of A is the following. There you have it. And that concludes example 2. Okay, so here we have theorem 14, which is also referred to as the rank theorem. And there's really a lot going on this slide, and you just kind of have to piece together all of the information and everything that's related. So let's try to piece this through together. The rank of A is the dimension of column space A. So take a moment, let that sink in. Sometimes we see the word nullity, and that is the dimension of the null space of A. Well, this theorem 14 says the dimensions of the column space and the row space are equal. This common dimension is known as the rank of A, and it equals the number of pivot columns, and rank A plus the nullity of A is equal to n, which are the number of columns of the matrix. Now you might be thinking, what? And I understand. So, you know, we kind of need to put this all together. So a couple things from here. Rank A is equal to the number of pivot columns. Okay, that's helpful. Some other things that you will come across. You will see that row of A, or let's say the dimensions of row of A, is equal to rank A, and that's stated here. And it is also equal to rank A transpose because of the dimensions of the column space. So row rank is equal to the column rank is equal to rank A. In other words, the dimension of row A is equal to the dimensions of column A is equal to rank A. Okay, so all of these things are the same. You are going to want to use this information in several homework questions, so keep that in mind. So let's use the rank theorem and talk about what's going on. You'll see problems like this in your homework as well. It'll say if A is a 7 by n matrix with a 2-dimensional null space, what is the rank of A? So we're going to use this rank theorem, and I want you to remember the rank theorem says rank A plus the nullity of A, and that's just the dimension of the null space, is equal to n. Okay, so let's think about what we know. Matrix A is a 7 by n matrix. So this is the number of rows and columns. A lot of times we say m by n, an m by n matrix, and that's what the theorem says. So we know that n is 9. We also know that there is a two-dimensional null space. That's the nullity. And we want to find out what the rank is. Okay, well, here we just have an equation. What plus 2 is 9? Well, it's 7. So 7 is the rank of A. Oops, that should say A. Okay, in the next part, we want to know if a 6 by 9 matrix, if it can have a two-dimensional null space. Okay, well, let's think about this for a second, okay? Let's, since this was matrix A, let's call this matrix B. Okay, so the rank theorem says the rank of B plus the nullity of B, nullity of B is equal to n, okay? Well, we have an m by n matrix, so n is 9. We want to know if it can have a two-dimensional null space, so that means this would be 2. So we need to figure out rank B. Okay, well, rank B would have to be 7, right? Because 7 plus 2 is 9. Okay, but let's think about this for a second. By the rank theorem, the columns of B are the vectors in R6, right? So the columns of B are the vectors in R6. So the dimensions of column B cannot exceed 6. So the dimensions of column B has to be less than or equal to 6, which means the rank of B has to be less than or equal to 6 by the rank theorem. So could this matrix have a two-dimensional subspace or null space? The answer is no, because of this. Okay. I put this example 4 on here. Go ahead and read through that. It's on page 236. This is the important part on this slide here. This will come up again. So if you have an m by n matrix, the null of A is in this space, row of A here, so on and so forth. Okay, so this is something that you will see in your homework. It will come up again, so make sure you pay attention to this. Some people like this illustration of the rank theorem. This is just something that was given to me. If you want to take a look at this, go ahead and pause it. This example here is directly from your text. What page is this? This is example 5 from your text, so page 236. Oops, 236. Rather than me taking the time in this video to go through it, just read through it. I think it'll make sense to you. Just consider the rank theorem when you're reading through it. And then finally, this is more of the invertible matrix theorem. So here, this now talks about an n by n matrix, so that's important. And then these items that involve rank and dimension of this n by n matrix. Okay, that concludes the information from section 4.6 and chapter 4. So begin preparing for your test. Good luck.